Welcome to Signals and Systems. Throughout this tutorial, I'd like to request you to pause the video whenever you need it and keep pen and paper with you so that we can solve problems to consolidate our understanding. In some of the lectures, we will play around with some of the signal processing ideas in MATLAB, so I'm assuming that you already have some level of exposure to MATLAB. We'll continue our discussion on classification of signals, specifically periodic and aperiodic signals. A common situation in signal processing is to have a signal that is sum of two periodic signals. Let's say you have a periodic signal x1 of t with fundamental period t01 and another periodic signal x2 of t with fundamental period x2 of 2. Now we ask, is the sum of these two periodic signals x1 and x2 also periodic? So let's say x of t is equal to x1 of t plus x2 of t, that is, x of t is the sum of these two periodic signals. Now whether or not x of t is a periodic depends on the relationship between the periods of t01 and t02. If we can find the time capital T that is an integer multiple of t01 and is also an integer multiple of t02, then capital T is a period of both x1 of t and x2 of t. Therefore, x1 of t is equals to x1 of t plus capital T, and x2 of t is equal to x2 of t plus capital T. That's from the definition of periodic signal. So if we perform simple shifting of this equation here, x of t equals to x1 plus x2, then we end up with this equation, x of t plus capital T is equal to x1 of t plus capital T plus x2 of t plus capital T. If we combine this equation and the equation here and here, we end up with the equation below, which says x of t plus capital T is equal to x of t, which is the condition or definition of a periodic signal. So from this we understand that if we can find an integer multiple of t01 and t02, which is capital T, then the sum of two periodic signals is in fact periodic. So the smallest positive value of capital T, that is an integer multiple of both t01 and t02, is called the fundamental period of x of t. So the smallest value of t can be determined by taking the least common multiple LCM of t01 and t02. If you're thinking in terms of frequency, which is the inverse of period, we can also take the greatest common divisor, GCD, of the two fundamental frequencies of the component signals x1 and x2 to obtain the frequency of the resultant signal. So this is an alternative method to determine the frequency or period of the summed signal. However, the equation shown here does not work if we cannot find an integer multiple of t01 and t02, and then the sum of two periodic signals becomes aperiodic. So it really depends on t01 and t02 what the sum will be. So the easy way to remember this is that we take the ratio of t01 and t02 and see if it's a rational number. That is, the ratio can be expressed as a fraction of two numbers. If we can do that, then the sum of two periodic signals should be periodic. If we cannot find if we find that the ratio of the two periods of x1 and x2, the constituent signals or the component signals, are is a irrational number, that is, it cannot be expressed as a fraction, then we say that x of t here, the sum of the two signals, is an aperiodic signal. So to summarize, if the ratio of the periods of two signals is rational, then their sum will also be a periodic signal. Now the period of the overall signal will be the LCM of the periods of the signal components we can use MATLAB's LCM command or function to determine the LCM of two numbers. And instead of period, we can also use frequency to determine the period or frequency of the overall signal, that is the summed signal. So the frequency of the overall signal will be the greatest common divisor, or GCD, of the frequencies of the signal components. You can also check out MATLAB's GCD command that helps us to compute the GCD of two numbers. Okay, so please pause this video and try to solve this problem, and then we'll match our answers. Okay, for problem number A, we see that it's a sinusoidal function. Now we're going to discuss sinusoidal function in the next lecture, but we already know that the general format of sinusoidal function is something like this: a sine 2 pi f naught t, or a sine omega naught t, where f naught is the fundamental cyclic frequency or linear frequency or general frequency, and omega naught here is the angular frequency. So we already know that all sinusoids are periodic with f frequency f naught. So here from this equation we see that f naught is basically 200, which means the period is basically 1 by 200, and g of t in problem A is actually a periodic signal. Okay, for problem B, you have a function 3 plus t squared. Now, so for this function, you don't have a pattern that gets repeated in every t seconds. So this is a monotonically increasing polynomial, and there is no pattern that gets repeated in every t seconds or something. So it's not a periodic signal; it's an aperiodic signal. Okay, the signal in C can be resolved into two components, into two sinusoids, using Euler's formula. As we know, Euler's formula says that e to the j theta is equal to cos theta plus j sine theta. So this is basically a sum of two sinusoids. Now we need to determine the frequency of this one and the frequency of this one, and then take the GCD to determine, and take the ratio actually to determine whether or not it's a periodic signal. So if we take the ratio of the periods or frequencies, we get 30 here, which is a rational number, which means the function in C is a periodic signal or function, and the fundamental period will be the GCD of basically 30 and 30, which is basically 30 hertz, and the fundamental period will be 1 by 30 seconds. Okay, the function in problem number D is again a summation of two sinusoids of 6 hertz and 9 hertz. The GCD of 6 and 9 is 3, which means the g of t here is a periodic signal with frequency 3 hertz or period 1 by 3 seconds. Now for problem E, we see that the ratio is not a rational number. The ratio of periods or frequency, whichever one you take, is 2 pi by 3, which cannot be expressed as a fraction, because pi, as we know, cannot be expressed as a fraction. So this is an irrational number, which means the signal in figure E is basically an aperiodic signal. So it's not a periodic signal. So hopefully you have a clear idea how to determine periodicity and identify periodic and aperiodic signal. Now we're going to see what even and odd signals or even and odd functions are. A real function x of t is said to be an even function if it follows this condition: x of t is equal to x of minus t. So this means an even function has the same value at the time instant t and minus t, t and minus t, for all values of t or time. So basically an even function is symmetrical about the vertical axis. So if you flip the signal, it remains the same. If you flip the signal with respect to the y-axis, the signal remains the same. Okay, and the real function x of t is said to be an odd function if it follows this condition, that is x of t is equal to minus x of minus t. So, yep. Okay, now any signal x of t can be represented as the sum of even and odd signals, such as this equation, x of t equal to x of even plus x of odd, where x of e here is the even component of the signal x of t, and xo here is the odd component of the signal x of t. So you might wonder, given that we know the signal x of t, how do we determine the even and the odd components of the signal? Let's say we know x of t, we want to find out what the even component and the odd components are. So what we do here, we replace t with minus t in the equation here, and we end up with this equation, x of minus t is equal to x e of t minus x odd of t. And then if we sum these two equations, this equation and this equation, and subtract these two equations, we end up with the expressions of the even and the odd components. So the even component is x of t plus x of minus t divided by 2, and the odd component is the x of t minus x of minus t divided by 2. So therefore, any signal can be decomposed into two components, the even component and the odd component, with this formula. Okay, now please pause the video and trying to solve this problem, and then we'll match our answers. Okay, so hopefully you've been able to solve this. So we already have x of t, we just need to determine x of minus t. So I just use this fact that sine minus x is equal to minus sine x, and cos minus x is equal to cos x. So using these two trigonometric identities, I determine x of minus t, and then I just put the values of x of t and x of minus t in the equations to obtain the even and the odd component of the original signal x of t. Okay, for b here, you find y of t first. From this equation we see that y of t is equal to 1 for t greater than 0, and y of t equal to 0 for t less than 0. So you find y of t first, and then you find y of minus t by replacing t with minus t in the equation, and then you simply sum the expression and divide it by 2 for each of these intervals to obtain the even and the odd components here on the right. Okay, now please pause the video and solve this problem, and then we'll match our answers. Okay, so hopefully you've been able to solve this. Okay, so now I'd like to summarize the classification of signals here. So a signal is classified as continuous time or discrete time based on the x-axis of the signal. So if the x-axis or the time axis is a continuous function, it's called a continuous time signal. If the time axis is a discrete variable, we call the signal discrete time signal. We can also classify the signal as analog or digital by looking into the y-axis. So if the signal has infinite possible values, we say that the signal is an analog signal, and if the signal can only take a few values, we say that the signal is a digital signal. Based on the power or energy values, we can also classify any signal as power signal, energy signal, or neither power nor energy signal. So if the power is finite, then we call the signal a power signal. If the energy is finite, we call the signal an energy signal. If neither power nor energy is finite, we call the signal neither power nor energy signal. If a signal repeats a certain pattern in a particular time intervals, it is called a periodic signal. And if a signal does not repeat a particular pattern in a particular time interval, it's called an aperiodic signal. If a signal only exists on the right side of the y-axis, it's called causal. If it only exists on the left side of the y-axis, it's called anti-causal. And if it exists on both sides of the y-axis, it's called a non-causal signal. If an expression or mathematical formula, if an equation is known, it's called a deterministic signal, whereas we only know certain statistical properties of a random signal or stochastic signal, and its equation is unknown. And an even signal is basically symmetric with respect to the y-axis, and for an odd signal is basically anti-symmetric with respect to the y-axis. Thank you for your time. If you have any questions, please feel free to ask in the comment section. Thank you.